I'm gonna start playing with Thor. I only have like 2 hours into it.
Okay. Well, if we can take a break from talking about video games to talk about work and power, that'd be cool.
I put in so much work and I had my power on.
Yeah, you're using all that power to do all that non-work. Okay, so we talked about energy. We talked about potential and kinetic energy for weeks now, basically since the beginning of the school year. Now we're going to talk about something called work and another thing called power. So first, let's review energy. This might be a new term, TME, or total mechanical energy. Total mechanical energy is the sum of kinetic energy and potential energy. So we remind ourselves that kinetic energy is the energy of what?
Motion.
Energy of motion. And potential energy is energy of stored, height, or stored energy. So kinetic energy is the energy in motion measured in joules. By the way, the guy back here, that's a drawing of James Prescott Joule. But kinetic energy is the energy of motion measured in joules. And potential energy is the energy of storage, also measured in joules. Now, there are lots of different types of potential energy. We'll learn one called spring or elastic potential energy later on. But just understand that we've been focusing on gravitational potential energy because that's the one that usually relates most well to kinetic energy. So we've seen these. Kinetic energy is 1/2 mv squared. 1/2 times mass times velocity squared is how much kinetic energy something is carrying. And then mgh is how much potential energy something's carrying. And when there's a kitty up in the tree, if the kitty's really high up, and we take the ground to be the reference point, the kitty has potential energy. And then when the kitty jumps down off the tree onto you, it loses its potential energy, and that potential energy converts into kinetic energy. And then as it lands on you, you notice, oh, it landed with all that speed, and it converted its potential energy to kinetic energy. And then the cat, does this thing on, meow. But when things fall, their potential energy turns into kinetic energy. Now, the reason we don't write weight as W anymore is because, close, we'll talk about watts later. The reason we don't write weight as W anymore, we write it as Fg, force of gravity, is because W is actually work. Work is the change in energy. Work is the change in energy, and we find it by applying a force over a distance. This is one of the most, not usually, usually distance is a small d. This is one of the most complicated, or actually one of the simplest concepts that for some reason people want to make really, really complicated. Work is force times distance. If you apply no force over a distance, you don't do any work. If you apply a force but not over a distance, you don't do any work. Okay, does that make sense? For instance, your chair is supporting your weight, but is it doing any work? No, because you're not moving in the vertical direction. Similarly, if I apply a force on this cabinet, but the cabinet does not move, do I do any work on the cabinet? No. And here's the one that bothers so many people. If I pick up this 2 kilogram mass and I hold it like that, am I doing any work? No. I'm applying a force. I have to apply a force against gravity, otherwise it's going to fall, but I'm not actually changing its distance. So no work is doing. Yeah, if I do this, then I'm doing work. Okay? So if I raise it up, then I'm doing work. If I just hold it there, I'm doing work. But Mr. Byers, your arm's going to get really tired. I know, but technically speaking, physically, if we're going to call work force times distance, and we are, then force over no distance does no work. Question?
Now, even if you ran like a 3K and you ended up in the same place, which would be 0 distance, your displacement would be 0, you'd have 0.
It's not displacement.
Yeah, it's not displacement, it's distance. Yeah, that is a really good point. It's going to be the actual distance you travel. So if you took it as work is force times displacement, then you could say, yeah, no net displacement, no net work. But let's not make it complicated. Yeah?
So work is force times distance or force divided by distance?
Times.
You're saying over.
Oh, what was I saying? Over?
Yeah.
Like I said, work is force times distance. Oops. Rewind. Edit out. Okay. So work is force times distance.
That makes sense why it's 0.
Yeah. Thank goodness you're here.
It's like net force equals no acceleration.
Okay. So if I got my my foam, I got my foam school bus right here, and if I raise it 1 meter over the table, let's say it's really simple. Let's say it has a weight of 1 Newton. If I raise it 1 meter over the table, and it has a weight of 1 Newton, then it's carrying a potential energy of how many joules? 1. Because mg, that's your weight, 1, height of 1. So if I raise it over 1, it's carrying a potential energy of 1 joule. When I drop it, that 1 joule of potential energy turns into 1 joule of kinetic energy right as it's about to hit the ground. In infinitesimally small time, as it's about to hit the ground, all that potential energy becomes kinetic energy. Make sense? Yeah. 1 joule of potential, 1 joule of kinetic. How much work was done by gravity? 1 joule, exactly. Because there was 1 joule of an energy conversion. Work is done anytime any type of energy converts to any other type of energy. In this case, potential to kinetic, 1 to 0, work did 1. Yeah?
I'm confused about why you want this put gravity to the account. So would it be 10 joules of potential energy with gravity?
No, I made the weight 1, not the mass 1.
Okay.
So I made the weight 1 Newton, not the mass 1 kilogram. If I used my, I don't know where it is, but if I use my 1 kilogram mass, then I would have 10 joules of potential energy.
Okay.
Yeah.
Can work ever be negative?
Absolutely. Because the question was, can work ever be negative? And absolutely it can, because we're talking about a change in energy. You can basically take energy and you can go to less energy or more energy. For instance, as gravity did a joule of work pulling it down, that joule of work was positive for potential to kinetic and negative from kinetic to potential. Does that make sense? It gained a joule of potential, or gained a joule of kinetic, but lost a joule of potential. I might be backwards all over the place today. It's Monday, so if I get backwards and I confuse you, please let me know. Okay. Does that make sense? Potential, kinetic. Okay. Yes.
So, how would you, like, if you plugged it in force times distance, how could you get a negative force? Like, you can't apply negative force or get a negative distance.
Yeah, because then you have to use displacement for a negative displacement. But again, don't make it more complicated than it has to be. All right, so here, I'm going to turn the lights on and I'll show you my newest rig. Yeah. You know what? Let's do the animation first, and I'll show you my newest rig. Pause. Back. Okay. So this is a scenario. I'd like you to talk for a minute with your neighbors. This is a scenario. You have a red ball and a blue ball, and you have 2 tracks, guys. And the red ball is going to fall a certain distance and it's going to cruise along, and the tracks are frictionless. Okay, so the red ball is going to fall a distance, then cruise along. The blue ball is going to fall that same distance, cruise along, then fall an additional distance, cruise along, then climb that same distance and cruise along. No friction. So I'd like you to answer these questions. Which ball, or this question, which ball will reach the finish line first? And while you do that, I'll set up my new rig. No.
It would definitely jump off.
It's not going to jump. All right. So, let's take a vote. With a show of hands, who believes that the red ball will reach the finish line first? 1. All right. 1. Who believes the blue ball will reach the finish line first? None. Oh, I can select. Is that influencing your answer? No. Okay. So who believes? So basically the rest of you. So 33. Okay. Let's find out.
We're all wrong.
It's gonna be the blue. No, it's gonna be red.
Oh, you were wrong.
What?
So.
It didn't even change speed. It didn't even look like it changed.
Oh, but it did.
Because there's no friction.
So look what's happening, guys. As I'm gonna grab the thing, pause it. As it's going down, it's losing what? Potential energy, and it's gaining what? Kinetic energy. So here they have the same speed because they have the same kinetic energy. So far, so good? But now look what happens here. The blue ball gains more potential energy because it loses additional potential, gains more kinetic energy because it loses additional potential energy. So lose potential energy, gain kinetic. Blue ball gains more kinetic by losing more potential. Now it has additional speed. So it's going to cover this middle section faster. When it gets to this point, the blue ball exchanges its additional kinetic for additional potential to get back to its original place, and now they're at the same speed again. So they're the same speed here, and they're the same speed here, but in this bottom section, the blue ball is faster. Let's pretend you chose the blue ball.
It's gonna trick us and not work. Yay. Yay. The nose on that smiley face is tripping me out. It's just all line.
I think it's a.
Looks like a double chin.
I think it might have something to do with the bad screen.
I've never seen a smiley face with better eyebrows than the black line looks like a smiley.
All right. I have something similar up here. And this worked, I promised this worked on Friday, so we'll see if it works again today. So this is what's going to happen. I'm going to put marbles or steel balls. Would you want to use black marbles or steel balls?
Steel balls.
Steel balls. Balls of steel. So I'm going to put balls of steel in these little grooves, and there are 4 of them. Ah, it's going to lose it. Oh, there it goes. Okay.
There's 4 of them?
Boop. Yeah.
Oh, I see them.
There are 4 tracks. Hey, get up there. The steel ball is heavy enough to push the my little foam truck down. Okay. So I got 4 tracks. The track closest to you goes like this. It goes straight and then swoop at the end. Okay. The second track is a straight shot. It just goes whoop. Although it has the same change in height. So let's draw it like they have the same change in height. The third track goes straight and then super steep. And the fourth track goes whoop. Okay? So, they all have the same change in height. So the potential energy up here is going to change into the same kinetic energy up here. And I sanded them down so they're pretty close to the same friction. So, chat with your neighbor. Which one do you think will get to the end first?
Are we gonna go to the skate park?
Oh, I wish. All right. All right.
Is this black still? Yeah.
All right. Let's take a vote. This is kind of fun. So, how many people think it's going to be the first track with the long and then the sloop? Nobody? How many people think it's going to be the gradual decline the entire time? Nobody. Oh, one? So nobody here. Nobody here? No. Nobody here. How do you think this is going to be the straight and then swoop and then straight again? One? So the rest of you think it's going to be the swoop and then long?
Yeah. Go against. I'm gonna be right again.
33. Okay. I'm going to pack some tissue in here so I don't break my little cubic meter here. Or cubic liter. Ready? It was the second one. Yeah, it was the second one. Ding, ding, ding. Okay, so that's cool.
I took back my answer, dang
You guys, you gotta believe in yourself. You're like, but she was always right. When we were growing up, she always had the right answer. Well, not anymore.
Mr. Byers,
Yeah.
didn't we just go through this and now it's
Oh, it has something to do far more interesting than you realize.
We just
But I'm not sneaky, but this is. Okay, so I want to show you something else. It's actually more important, and we'll explain why you got it all wrong. Okay, you ready? Yeah. I've rigged up a photo gate, and I've set the photo gate to only be blocked with the diameter of the ball, which is about 1.5 centimeters. So the little balls are about 1.5 centimeters. And I want you to notice something kind of interesting. I do need a volunteer to hit the collect button over there. Okay, Jason's on the case. So, yep. Go ahead and hit collect and then it'll wait for me. So, yep. Here we go. Okay. Now hit the finish button. Okay. Cool. Okay, it works. What this did is it calculated the velocity of every time it was blocked. In other words, how long it was blocked into how wide I told it to be. And you'll notice something kind of interesting. Look at the velocities. 1.88, 2.0, 2.0, 1.88. You want to try it again? They're not very different. What's important is they are the same, taking into account a little bit of friction and things. If we kept doing it and kept doing it and kept doing it, we would constantly get the same about 1.9 meter per second, 1.9 meter per second, 1.9 meter per second. Do you want me to do it to prove it to you, or you just want to take my word on it?
Do it. Do it.
Do it? Okay. You're like, whatever takes the longest, Mr. Byers.
No, well, of course not.
Whatever requires us to write the least notes. Okay. So, Chase? So, 2.1. Oh, but look, these switched places.
What?
Yeah. Maybe one of the balls is slightly wider than the other ones. But the important thing is, guys, the important thing is they have the same velocity. Why? Why do they end up down here with the same velocity as up here?
Because they're losing.
Exactly. They're losing the same potential energy. They travel from the same height here down to the same height here. So they're losing the same potential energy, so they're gaining the same kinetic energy, and they're the same balls. Yes?
The way you just did on the other thing, like the other, I don't know, the other simulation with the blue ball and the red ball, I thought it would be the first one because it goes down the farthest, so it would gain the most kinetic energy.
And here's what you didn't realize about this. Take a look at those 4 tracks. They do end up with the same velocity, and this one back here does get faster. But this one starts speeding up, and what do you notice about track 2? No, look at the design. It's not only straight, it's also starts with a sh and ends in order. It's shorter. It's a straight shot. Remember you probably learned when you were 4 years old that the shortest distance between 2 points is a straight line when you're playing tag. Okay, so the second track is a straight line. So yeah, this one, the track in the back got faster first, but it had to cover a lot more distance. So yeah, the takeaway from this, and what's the most important is, since they have the same height, they are going to have the same speed down here. And the reason why you got that part wrong, that first part wrong, was track 2 is a straight shot. Track 3 gets faster right away and gets to its maximum speed right away, but it also has to cover a lot longer distance. Track 1 takes a long time to cover get to that maximum speed. And track 2 has this whole distance right here where it's going really slow, then it gets to its maximum speed, then it slows down again. Question?
So the only reason why the straight ones get there first because there's less distance.
Mm-hmm.
It's just that's it.
Exactly.
Okay.
But the takeaway from this, it's most important, is same height, same speed. Okay? So let's just try this for fun. I'm sorry, what?
Wait.
Yeah. Okay, 1 then 2. You first.
Okay, did the blue ball have the same amount of distance to travel as the red ball?
No, but it covered that. It covered the up and downs. Those were basically considered to be the same distance, the overall distance. So let me explain what I mean. In the track, it went down and then up again. It basically took this distance. The computer took that distance to be the same as the across distance. So effectively, it was the same. Yeah.
Okay, so all of those are the exact same length?
No.
No. Okay.
The straight shot is a lot shorter because there's no curve.
Okay. If you had, because it would be a longer length, but if it started at the same height and ended, if you twirled it, would it still do the same thing?
It would still end up with the same speed, but it would take a long time to go down there. Yeah. It would still end up with the same speed because the change in potential energy is the same. Okay, next. I still need you right there, Chase. So these are steel balls, and these are glass marbles. Steel has a lot more density than glass. Turns out. So if you're going to repel the British invasion, you want to use metal balls, not glass. So this is what we're going to try. I do know that the glass marbles are slightly larger because I have a digital vernier caliper. So the marbles are actually 16 millimeters, not 15 millimeters. So just so we're all square, I'm going to go ahead and change the width of the marble. You can see right there. Okay, or move. I'm going to go ahead and change the width of the marble, see if it allows me to change it by hand. Yep, there we go. Okay, so now the width of the marble is at 6. Let's see if we get the same 1.9-ish meter per second. Yeah, all right. So let's just try this again. I didn't actually check this because I just got this yesterday, Friday, and I was sanding it all weekend. But I sanded it over the weekend. Do you think by using a less massive ball that the speed should change at the end?
Well, they'll all have the same speed.
Yeah, now we went from 4 steel balls to 4 glass balls.
They'll have the same speed at the end, but maybe they'll
Let's find out.
Probably not.
Well, let's take a vote. So let's see, we're talking about the speed of glass, V glass, versus V steel. And we could do larger than, equal than, or smaller than.
It's gonna be lower.
No, the potential energy is based on
Yes.
mass, gravity, height. Bigger mass equals more potential.
Okay, so the conversation is, since the steel ball has more mass for approximately the same volume, for the steel ball has more mass, it would have more potential energy. So then it would have more kinetic energy at the bottom. So you expect it to go faster? Interesting. Okay, let's give it a try.